Hello and welcome to the hands-on data science project on credit card fraud detection, model building and deployment. In this project, we are going to cover a use case where we have to detect whether a credit card transaction is a legitimate or fraud using machine learning models. This will help banking institutions to put proactive monitoring and fraud prevention mechanisms in place. So, we will follow a step-by-step process to first analyze and understand the data, which consists of 284,000 transactions around, then create and evaluate different machine learning models and data processing techniques to find the model which performs the best. To achieve all this, we are going to use Python as our programming language, Jupyter Notebook in Google Colab to write, execute and visualize our Python codes, NumPy and Pandas for performing data analysis, sklearn libraries for model building. Yes, we have a lot to cover. So without further ado, let's get started. In this video, we are going to look at the problem statement once again in little bit more detail, and also we are going to detail out the steps that we are going to perform in this whole exercise of model building and evaluation. So let's look at the problem statement in little bit more detail first. For many banks, retaining high profitable customers is the #1 business goal. Now, banking fraud, however, poses a significant threat to this goal for different banks. In terms of substantial financial losses, trust and credibility, this is becoming a concerning issue for both banks and customers alike. Now, in the banking industry, credit card fraud detection using machine learning is not only a trend, but a necessity for them to put proactive monitoring and fraud prevention mechanisms in place. Machine learning is thus helping these institutions to reduce time-consuming manual reviews, costly chargebacks and fees, as well as denial of legitimate transactions. In this project, we will detect fraudulent credit card transactions with the help of machine learning models. We will analyze customer-level data that has been collected and analyzed during a research collaboration of Worldwide and the machine learning group. Now, let's understand a bit about the data. The dataset includes credit card transactions made by European cardholders over a period of 2 days in September 2013. Out of a total of 284,807 transactions, 492 were fraudulent. So this dataset is highly unbalanced, right? With a positive class, that is frauds, accounting only for 0.172% of the total transactions. Now the dataset has also been modified with PCA or Principal Component Analysis to maintain confidentiality. Apart from time and amount, all other features from V1 to V28 are the principal components obtained using PCA. The feature time contains the seconds elapsed between the first transaction in the dataset and the subsequent transactions. The feature amount is a transaction amount. The feature class represents class labeling, and it takes the value of 1 in case of fraud and 0 in others. Now, these are the broad level steps that we are going to perform in the entire exercise. First, we are going to import the dependencies. Then we'll do a EDA or exploratory data analysis. Then we are going to split the data into train and test set. And then we are going to perform model building with different techniques and strategies. We'll be using cross-validation with repeated KFold. We'll be using cross-validation with stratified KFold, and then random oversampler with stratified KFold. Then we'll be using SMOTE techniques, ADASYN, and finally we'll do the hyperparameter tuning on the model which performs the best. And then we'll arrive at a conclusion to understand which model performed the best and what conditions. And we are going to use these techniques on all the different models, like starting from logistic regression, random forest, k nearest neighbors, decision trees, SVM and XGBoost. So let's look into next video and understand how we can import the dataset, and most importantly, we are going to use Google Colab in this entire exercise. So let's go take a deep dive and understand how we can import this entire dataset and the notebook in the Google Colab and execute it. Now there are two ways you can handle this about the package installation. One is if you are executing in your local machine, either in your laptop or in your home PC, Then you can install all the dependencies that will be required to work on this project using this requirements file, which I have kept here in the code. So this file I'll be attaching at the end of the session. You can download from there and you can trigger it to install these dependencies in your machine. So let me open the file. So these are the dependencies that will be required. So NumPy, Pandas, XGBoost, scikit-learn, matplotlib, Seaborn, SciPy, and stats models. So these are the libraries or packages that will be required, which will help you to execute this file or this project. So you can go ahead and install each of them one by one, or you can open a command prompt and hit pip install -r then space requirements.txt. This will install all these packages for you in the background with the help of one command. So this is how you're going to install these packages if you are doing in your local. But if you prefer to use Google Colab, which comes completely free, and then you don't have to install all these packages at all. So for this project I've used Google Colab. There are two reasons behind it. So the reason being, it is a very intensive process because you're dealing with 1,47,000 close to data. So whichever model you run, it will take a lot of time if you don't have sufficient computational bandwidth in your, which you most of you don't have in your local machines, right? So if you use Google Colab, it will run, maybe it will take the same time, but in your local machine you can do some other work. It will not stop you from doing other works, because if you're running in your local, it takes a lot of RAM, and which sometimes stops you from opening other processes or doing multitasking things in your laptop or in your personal machine. So I'll recommend you to use Google Colab for this exercise if you are intending to run this notebook along with me. Okay, so if you're using Google Colab, let me guide you how you can use it if you're doing it for the first time. So go to Google Drive, right? And then create a folder called Colab Notebooks, right? And when you create this folder Colab Notebooks, then place the credit card fraud detection IPYNBY or the notebook file in here, upload it in here, and the credit card.csv, that is a data file on which you are going to work, also in the same folder. These two files again I will be attaching at the end of the session. You can download from there and you can upload it here. And once you do that, just double click on it. This will open it in a new tab, and then you have to go here and click on connect. Okay, so you can just click on connect here. That will also do, and I'll not go through all these options because we will be deviating from the topic then. Okay, just click on connect. It will connect with the Google runtime, and then in the post that whatever cells you want to execute, you just click on the run cell and it will execute the cell for you. All right. So in this way you can use the Google Colab in the entire exercise. In the next session, we are going to cover how you can import these defined packages and what are the significance of these packages. Now in this video, we'll understand the libraries that needs to be imported. So we'll be using either the Google Colab or the Jupyter Notebook that I have in my local machine interchangeably, because both are the same notebooks that I have here with the same line of codes, right? So here, if you see that we are first importing the NumPy, the Pandas, then the Matplotlib for visualization, right? The Seaborn as well for visualization, then the SciPy libraries for the box cogs. I think these are not being used in the project currently, just kept it because I was trying out multiple things. And sklearn for all the models, for all the pre-processing libraries like the standard scaler, for all the model evaluation libraries like the classification report, confusion matrix, ROC curve, and for the trend test plate, the grid search, randomized search CV that we'll be using to do the hyperparameter tuning, and then all the different models, right? All part of the sklearn package, like the random forest, otherBoost, decision trees, logistic regression, k-nearest neighbors, and the XGB or the XGBoost comes with a different package, right? And hence the XGB classifier is part of that package, also the plot importance, and we will be again using sklearn for otherBoost classifier. right? So these are all the different libraries that we'll be using across to accomplish our model building and evaluation process. So now in the next session, we are going to take a deep dive into the exploratory data analysis part. Now let's import the data from the source. Now if you're doing in your local machine, right, if you're using your local machine to execute this piece of code, then you can simply do df pd.read csv and you can put it in this way, which line which I have commented, right? But if you're using Google Colab, then you can use this piece of code. First you have to write from Google Colab import drive.mount contain G drive, right? And next, once it is mounted, it will ask for your one time random key which is generated. Again, it will come as a hyperlink, which if you click, it will generate your code in the Google itself, and then you have to paste that code. So this is all pretty self-explanatory. Once you execute this piece of code in your Google Colab, you will understand. Post that is done, then loading the data. So you have to use something like this. The pd.read csv is same if you do in local to what you do in Google Colab. The only difference comes from where you're importing it. So G drive / my drive, till now this is common for everyone. Then Colab notebooks, you remember one folder we have created in Google Drive before we have started, that's the Colab notebooks. And then /creditcard.csv, the CSV file name which contains the entire data set, right? Once you do that, you do df.head and it prints the first 5 rows from the data set, which you are going to talk about in detail in the subsequent sessions, what each column is and all. Now that we have imported the data set, let's go ahead and try to understand a bit about the data. So as we have seen earlier in the earlier session, I have done df.head to print the first 5 rows of the data set. Next, I'm doing df.shape to check the number of rows and columns that exist in the data set. So there are around 284,000 data and there are 31 columns, which you can see it here, right? Then we are doing df.info to check the different all the columns, how many null values are there in each of the columns, and also the data type of each of the columns, right? So we see that all the columns having no null values, that's what it says, non-null, right? So here we see 284,807 data for against all, and the data type for each we can see here, mostly a float except the class one, which is our target variable, which is in integer data type. Next we do df.describe, which gives us some statistical numbers of the mean, of the minimum, of the 25, 50 and 75 percentile, and we see the distribution of all this data of all these columns against these statistical measures, and we get these values. This helps us to understand the distribution of the data set, okay, of the data in the data set. Okay, in the next session we are going to see how we can find out the percentile of the of the number of transactions which are fraud versus which are authentic or which are genuine transactions or good transactions, right? So let's dive into the next session to see how we can perform that. Now let's go ahead and check the class distribution of the target variable. That is how many cases of fraud and how many are legitimate transactions. So the target variable is the class. So we are doing value counts to get the distribution of the legitimate and the fraud transactions here. And now we are using these lines of code to derive the percentage of this distribution of the of the target class, that is legitimate versus fraud. So we are using group by of the data frame method, and we are passing the class target variable, and we are taking the count of each of the distribution, right? One is fraudulent and one is legitimate, and then we are dividing the total number of values in the target variable or total number of rows in the target variable, and then multiplying by 100, which gives us the percentage against each of the fraudulent and legitimate, right? Next we are using the same piece of code, and this time we are using .plot.py to derive a pie chart out of it, just to visualize the distribution of the fraudulent versus the legitimate transactions. We can derive the percentage in a slightly different way, which I have put down here just for your understanding purpose. So we can similarly we can use dot value counts again to get the distribution of the classes of the number of counts in the 0 and number of counts in 1, and then we use classes the first index divided by that entire class value dot count, which will give us the total number of rows into 100. And we are doing the same for fraud, that is class 1 is the fraud, so right, dividing by the total number of rows in the class column and multiplying by 100, which gives us again the same number, that is 99.82 is the legitimate transactions and 0.172 is the fraud transaction. So so we see that it's highly unbalanced, right, which we have already covered in the earlier sessions. And we will use the same two numbers to plot a bar chart now. We have plot pie chart earlier. Let's plot a bar chart. For that we are using the Seaborn library's count plot function, and we are passing the class column to it, and we are setting the title as class count. We are setting the X label as record count by class and the Y label as count, and we are setting the font sizes, and there we are doing plt.show. So count plot automatically takes care of the number of counts in each of the zeros and ones, and plots the bar chart accordingly. So in this way you can derive the percentage using both of these methods, this one which I have shown here, and also this one single line which you can see here, right? And then you can plot a pie chart or a bar chart as per your need and requirement. Now let's try to understand the correlation between the features and then plot a heat map of it. So I'm going to use dataframe.correlation function, CORR, and when we pass the entire data frame to it, it puts something like below. It shows for each column or each feature how it is correlated with another feature. Negative means it's negatively correlated, and positive means there's a positive correlation, right? So here we can see the entire correlation, but sometimes what happens when we have a lot of features and a lot of numbers, is as in this case, it's very difficult to visualize how strong or how weak the correlation is between the features. So it is very obvious to plot an heat map of it. So I'm using sns.heatmap, and we are passing the correlation object that we have, which we got here. And once we do that, and we are just setting CMap as schoolworm, there are a lot of other options that you can try. You can check the SNS heatmap libraries once if you do Google, you will find out all the different CMaps available out there. And we are setting the annotation as true, which prints out the values, right? And then we are doing plt show. If you see this figure, you want to see it in a bigger way, you can change the fixed size here. Okay, and if you see here, the dark blue shows is strongly correlated, and the light blue shows it is not so highly correlated, right? So you can see here 0.12, right, time with this feature V12 is very weakly related to, however V2 with amount is very strongly correlated. See the deep blue. So in this way we can see the correlation matrix, and also with the help of heat map it helps us to better visualize the correlation, right? In the next section we are going to talk about feature engineering. We will see how we can derive new features from existing features. Now let's perform some feature engineering. So if you remember the time feature that we have, which contains the seconds elapsed between the first transaction in the dataset and the subsequent transactions. So we are going to use a function called, let me scroll down to this area. Yeah, so we are going to use a function of pandas, which is time delta, which represents the duration, the difference between two timer dates. So we are going to put something like this. So we are going to use 2 time delta, and it's a pandas function. So pd.2 time delta, and we are going to pass to it the time feature to it, right? And the unit is in seconds. So once we do that, we get the resultant output in delta underscore time, and we are going to access delta underscore time dot dt dot components dot days, which will give me the time of the day. And also in the similar fashion, we are going to extract the hours and minutes. Okay, so at the end we are going to convert the time feature into and break it down to 3 features: the time underscore day, time underscore hour, and time underscore minute. Next, we are going to drop the unnecessary columns, that is the time, because the time feature itself we have converted into or derived into 3 features, independent features, so there is no need of keeping the original feature, so we are going to drop the time. And because I've tried out multiple things before coming up to this model, which I'm going to show you later, I found that time underscore day and time underscore minute is not adding sufficient value if I keep those features, so hence I dropped it. I dropped the time underscore day and time underscore minute. I only kept time underscore hour feature. Okay, and I think you are aware of how to drop a particular feature. df.drop, and you pass it, and you pass the axis as 1, so that means you are dropping the entire feature or the entire column, right? So this is the way you can drop. In the next session, we are going to see how we are going to split the entire dataset into a train and test dataset. Post that, we'll start off with the model preparation. In this session, we are going to cover train test split. So as you remember, class is the target variable, so we are keeping the target variable in y. And next, we are keeping everything in the x apart from the target variable. So in the existing data frame, from the existing data frame, we are dropping the class, and that gives us x, right? So next we are printing the x.head to just see whether the split of x and y worked. And if you see here, we don't have the class, right? So, but if we do y.head, we get the class, only the class. After this, we are going to use a train test split function. We are going to give it x and y, which we have splitted here, and we are setting the test size as 20, 0.20, which means test size is 20% and train size is 80%. And once we do that, we are just checking the sum of y train and y test, just to see whether the train test split worked as expected. The total number of values in y was 492, of which y train is 496 and y test is 96, right? So this brings us to a conclusion that train test split worked. Okay, in the next session we are going to cover the how we can see the distribution of a variable, right, and visualize it, and then we are going to finally move to the model creation part. Now let's cover the session on plotting the distribution of the variables or of the features. So first we are going to take all the column names or all the feature names into calls variable. Next, we are going to use df.class equal to 0 to get all the normal records, and df.class equal 1 to get all the fraud records. Next, we are going to go through each of the columns and we are going to plot a distribution, okay, or a histogram, better to say. So we are going to use Seaborn's displot function to achieve the same. So we are using the enumerate function here to go through each of the columns, and then use the displot to plot the distribution or the histogram for each of the columns for all the normal records in color green. And similarly, we are going to again use the displot for printing the histogram for all the records which are fraud, right, for each column. So at the end, we are going to get for each feature or for each column the distribution of all the normal records and also the distribution of all the fraud records in green and red color respectively. This will help us to understand how the data is distributed, how better to say how the target variables data is distributed for each of the features, and it will help us to understand whether there are skewness in the data, right? So in this way, this piece of code can help you to achieve this, what we have discussed just now. So let me go show you. So in some cases you will see there are a lot of skewness in the data. Some are left skewed, some are right, and some are normal distributed, right? And it has been done for all the features against the target variable. So in the next session we are going to cover the model building part. Before we start off with the model creation part and evaluation part, so it is very important to understand a couple of metrics and parameters which are very much important in the model evaluation phase. First is the confusion matrix. So what is a confusion matrix? A confusion matrix is a table that is often used to describe the performance of a classification model or classifier on a set of test data for which the true values are known. Now, if you see the table on the left, so this is how a confusion matrix looks like. You have the true class and the predicted class here on the x and y axis respectively, then the positive and negative, then the negative and positive here, right? True positive, false positives, false negatives and true negatives lined up respectively. So what are these true positives? True positives are basically where the observation is positive and the model classified it as positive. False negatives are the ones where the observation is positive, that is the actual is positive, but the model classified it as negative, right? So once you build the model, once you do the prediction on it, so that is coming as negative, but the actual is positive, right? So that those comes under the false negatives. Now what are false positives? That is this, right? So where the observation is negative, but the model classified it as positive. And finally, what are the true negatives? Where the observation or the actual result is negative, but the model that we created has classified the data point as negative. Okay, so in this way, the true positive, false negatives, false positive and the true negative, is defined. Now, let's move on to the next part, which is the classification report. Now, what is a classification report? It's a performance evaluation metric in machine learning. It is used to show the precision, recall, F1 score and support of your trained classification model. So once you build the model, if you have to evaluate how the model performs or how well the model is built, so this classification report can help in telling us precisely that. Now, what is a precision? Precision tells us how many of the correctly predicted cases actually turned out to be positive. Precision is given by this formula, that is true positive divided by true positive plus false positive. Now, what is recall? Recall tells us how many of the actual positive cases we were able to predict correctly with our model. Now, recall is given by the formula as true positive divided by true positive plus false negative. Okay, and finally the F1 score. F1 score is a harmonic mean of precision and recall, and so it gives a combined idea about these two matrices. It is a maximum when precision is equal to recall. So this is all about the classification report, which is again a evaluation metric which is used to show the precision, recall, F1 score, the support of your trained classification model. Finally, let's talk about the AUC ROC, which is very, very important for the classification based problems in machine learning. So what is AUC? It stands for area under the curve of receiver operating characteristics, also known as ROC. So the receiver operating characteristics ROC curve is an evaluation metric for binary classification problems. It is a probability curve that plots the true positive against the false positive at various threshold values and essentially separates the signal from the noise. So the area under the curve is a measure of the ability of a classifier to distinguish between classes and is used as a summary of the ROC curve. So the higher the AUC value, the better the performance of the model at distinguishing between the positive and the negative classes. So now that we have covered some evaluation metric, in the next session we are going to see how we can write a code, a common piece of code to print the confusion matrix and all other supported values. So with the help of that function, we can call that function multiple times whenever we build a new model, and that will act as an evaluation parameter for the model that we have created. Now, as we discussed in the last session that we are going to create a common function for the confusion matrix, so we are going to cover that in this session. So why this common function is required? Because what happens is that whenever you create a new model, you have to write couple of lines of code to print the confusion matrix, okay, or to visualize the confusion matrix, which will help you to understand how well your model is performing. So it is very annoying every time you're writing 4 to 5 or maybe 10 lines of code to achieve the same functionality, right? So it's better to put that into a method so that you can just call the method, passing some parameters to it, and it will give you the confusion matrix, right? And we have taken the similar approach for other areas as well, which we are going to see in subsequent sessions. So first thing first, we have created a data frame called df_results. We have used pd.dataframe to convert this into a data frame. So what we are doing essentially, we have created our empty data frame with all these column names, that is methodology, model, accuracy, ROC value, threshold. Just understand that this will be required to store all the results that we'll be creating. So we'll be creating many models using different strategies, so or different methodologies. So this df_results will store all the results for all the models that we are going to create, which will help us to compare at the end that which model is performing better than the other, right? So this is just an empty data frame, df_results. Now next we see the code for or the method for confusion matrix. So we have named the confusion matrix as this, and we are passing two parameters, y_test and pred_test. Okay, y_test is the actual and pred_test is the predicted value, right? And then we have used the confusion matrix function. We are passing y_test and pred_test to get the confusion matrix. Now we want to print the confusion matrix in a particular way, which looks very good and which gives a very good snapshot of the result. Though this will also, if you print CM, this will also fulfill the purpose. We want to make it visually good. So something like this. If you see this screenshot here, which I have taken, I want it to be something like this. So for that, to achieve that, I have written this piece of code. Okay, so first is the category names. So if you see in this image, the non-fraudulent and fraudulent, in this way I have named the the different sections. So I've defined the non-fraudulent and fraudulent here in an array. And next I printed the title, confusion matrix test data, which is coming up here, and then the X label and the Y label, which is here and here respectively, and below which didn't came up. Next I'm setting the ticks in np arrange lane category names, which is 2 in this case, as I have 2 values in this array. Next I'm doing plt.xticks ticks category names with a rotation of 45 degrees. And then plt.yticks ticks category names, which is here. Okay, and I'm setting the variable s equal to tnfp fntp. So tnfp fntp, and now I want to print the values, these values, right? 5 6 8 4 9 12, all these values I want to print it here. So for that, this line of code, so I am looping 2 for loops, one for I going through I range, and one inside that going through j in range 2. So each loop will be running 2 times, and inside each what I'm printing, basically CM is the confusion matrix. I am just extracting the values of the confusion matrix in this order with a font size of 12, and this gives me the values in this way. So this piece of method, if whenever we call, we have to pass the y_test and pred_test. Y_test is the actual value, pred_test is the predicted value. Once we do that, we get this confusion matrix in this format. So this is all about the confusion matrix function. In the next sessions, we are going to talk about other models that we are going to make and the common functions that we are going to create. Before we start with the common function creation for each of the models, it's very important that we understand the basics of this model. So we are going to use logistic regression, KNN, k-nearest neighbor, decision trees, random forest, SVM, XGBoost. So these are the models that we are going to try out across different scenarios in our problem statement here. So let's go through each of these models in at a very high level to understand what this model is all about. And in the next session, we're going to take a deep dive into the common code creation for each of the models. So first model that we're going to talk about is logistic regression. So logistic regression is one of the most popular machine learning algorithms, which comes under the supervised learning technique. It is used for predicting the categorical dependent variable using a given set of independent variables. Next, let's talk about KNN, which stands for K nearest neighbor. It is again a supervised machine learning algorithm. The algorithm can be used to solve both classification and regression problems. Now remember, this is a classification problem that we are solving in this problem statement that we have. The number of nearest neighbors to a new unknown variable that has to be predicted or classified is denoted by the symbol K. Now decision tree classifier. Decision tree classifier is a supervised learning technique that can be used for both classification and regression problems, but mostly it is preferred for solving classification problems. It is a tree structured classifier where internal nodes represent the features of a dataset, branches represent the decision rules, and each leaf node represents the outcome. Next, let's talk about random forest. A random forest is a machine learning technique that is used to solve both regression and classification problem. It utilizes ensemble learning, which is a technique that combines many classifiers or many decision trees to provide solutions to complex problems. XGBoost is an optimized distributed gradient boosting library designed to be highly efficient, flexible, and portable. It implements machine learning algorithms under the gradient boosting framework. It provides a parallel tree boosting to solve many data science problems in a fast and accurate way. And it is very popular in machine learning community, and it is one of the most used algorithm in any computation that you come across, and is very popular in Kaggle as well. SVM stands for support vector machine, is a supervised machine learning algorithm that can be used for both classification and regression problems. However, it is mostly used in classification problem. In the SVM algorithm, we plot each data item as a point in n-dimensional space, with the value of each feature being the value of a particular coordinate. Then we perform classification by finding the hyperplane that differentiates the two classes very well. So these are all the methods that we are going to use in the upcoming sessions to create the common functions for each models. So I hope this all descriptions was a very high level overview, which I think gave you an idea about the different models and what are the objective of those models, and in the next session we are going to see how we are implementing the same. Now that we have understood the basics of the models that we are going to create, now in this session let's start to create a model, a common function for each of the model types. This function will cover both the model creation and the evaluation code. So let's start off with logistic regression. So for logistic regression, we have created this method build and run logistic models, and we are accepting 4 to 5 different parameters. One is the df result, the methodology, xtrain ytrain, xtest ytest. Okay, so we are importing the sklearn linear model from the sklearn library, and then also the KFold. Right now, here numC is a regularization. Now if you have to understand all these different parameters that we are passing as part of the logistic regression model building, you can go through the documentation here for all these parameter details, right? So here numC will be used as a value for CS. Now CS is basically the inverse of regularization strength. So that means the smaller the value of CS, the stronger is the regularization, right? So we are setting using KFold for, we have to pass cross validation. So we're using KFold for that with n speed 10, which shuffle is true. Now we are calling the logistic regression CV model from linear model method. So then we are passing these parameters, that is the CS we already discussed, the penalty as L2, the scoring is on ROC AUC, the CV we discussed. I am passing the KFold, random state max iteration is 10,000, and solver is Newton CG, right? So, and the toll, if you want to understand what toll is, so toll is the tolerance for stopping criterion, toll is 10. Now this has been done for L2. L2 is the penalty, right? So we want to do the similar thing for L1 as well. So we have created a similar code for just changing it from L2 to L1, and then we are fitting both search CV L1 and search CV L2, right, on X train and Y train. Then we are printing the max AUC ROC for L1 and L2 using these two lines of code. Next, let's proceed with the parameters for L1 regularization. So once we have fitted the L1, so we are just printing the coefficients and the intercepts, and also printing the scores. Post that, we are doing the same for L2 regularization as well. Now once we have done that, let's do a prediction of both the models that we have created for L1 and L2 on X test, and we store the values in ypred L1 and ypred L2. Now with the help of this, okay, so before we move to the evaluation part which starts here, we are also getting the predicted probabilities, because this gives the predicted values, and we also want the probabilities here. So we are using predict proba function to get it, and we store it in ypred probs L1, ypred probs L2 for L1 and L2 model. Now comes the evaluation part. So remember, this common function that we have created is for both model creation as well as model evaluation for logistic regression L1 and L2. Now let's start with the evaluation. So we are getting the accuracy for both L1 and L2, right, and we are passing the ypred L2 ytest and ypred L1 and ytest for L2 and L1 accuracy, getting the accuracy, and we are using the accuracy score method to get the accuracy. Post that, for L2 model we are printing the accuracy, and we are generating the confusion matrix. Remember the confusion matrix function that we have covered in the earlier session, the method that we have created, we are calling that method and passing ytest and ypred L2. That is the actual and the predicted values that we have got above. And then we are also printing the classification report. Remember the classification report, we have discussed what it is and all in the earlier sessions. Similarly, we are printing the classification report, passing ytest and y prediction of L2. This has all been done for L2, right? And now we are proceeding with the confusion matrix. We are plotting the confusion matrix, and then we are printing the classification report, and then we are printing okay, so we are printing the classification report for L1. So all is done for L1 and L2 here. So the code, if you see carefully, the code is exactly the same for L1 and L2. Okay, now after that we move to print the ROC value for L2. Okay, we do it here in these two lines, and then we extract the thresholds using matrix.roc curve. A matrix.roc curve is a function, right, of the sklearn package, and we pass y test and y probability, predicted probability of L2 model. Once we get the threshold, we print the threshold, right, and the same exact piece of code I think we'll be using here as well to get the threshold as well as the ROC value. So here in this piece of code, here we are extracting the ROC AUC and we are plotting it. So we are plotting the ROC AUC curve here, and we are doing the same for L1 as well. So whatever we are using, maybe we are printing the ROC AUC curve, or we are extracting the threshold, or extracting the ROC value, we are doing for both L1 and L2 respectively. Finally, when we got all this, so we are, remember the df_results data frame that we created or initialized before we started with the model common function creation, which stores basically what methodology we are using, what is the model, is it logistic regression or KNN or SVM, so those models, and the accuracy, whether it's what is the accuracy of that model, and also what is the ROC AUC value of that model, and the threshold that we got. So all values we have got above, so we have stored it, and we are using dfresults.append to append into the data frame these values, and this has been done for L2, and similarly we are doing exactly the same thing for L1. Right, that's storing the accuracy for L1 model, ROC AUC, threshold, and all other respective values. Once we are done storing the values in df results for both L1 and L2 model, we are returning it. So whenever we call this function, what happens? Passing these parameters, so it builds the model, it does all the evaluations, it prints the evaluation and stores the key artifacts in the df result data frame and returns it back from where it is being called. Now that we have understood about logistic regression, the model creation, the evaluation code, the common code, remember, if whenever we need to call, or whenever we need to build a logistic regression model and evaluate it, all we have to do is call this method. Now we have to do the similar thing for other models as well. So in the next session, let's take a quick look for the next model, that is KNNs. So in the last session, we have covered the common method creation for logistic regression L1 and L2 and the evaluation code as well. Now in this session, let's take a look at the KNN models, or K nearest neighbor. Right, so we have defined this method as with the name as build and run KNN models, and we are passing these parameters df results. Df results, by now you understand, the consolidated result of the models that we have created, and with the accuracy score, with the ROC AUC value, with the methodology value in it. So we are passing to it to this method as a parameter. Not only to this, all of the methods that we are going to create, we are passing this as a parameter. The reason being, when we select a particular methodology and want to run all these models, or want to create and evaluate all these models for that methodology, it's very important that we stored the results of the earlier executed models. So whenever we execute the earlier model, say logistic regression model we have triggered, and then we want to run the KNN model, so we have to store the df results with all the values of logistic regression, and then we have to store it for KNN models as well. So we have to pass the df results variable or the data frame to this method, so that we can store and pass on the existing values and help this model, or help this method to store the or append the values to the existing df results data frame. Now methodology will cover in extensively what is methodology and what are the different methodologies we are going to use. Xtrend, Ytrend, Xtest and Ytest is pretty much self-explanatory. Now we have defined k nearest neighbors classifier with n neighbors as 5, n job 16. So we are considering 5 neighbors here, okay, and again this can be an hyperparameter. You can try out different values to find out which one performs the best for you. So knn.fit xtrend ytrend, this is to fit the model, and then we are extracting the score in the score method, and we are printing the model score here, right? Okay, so here we are printing it. Next, we want the accuracy of this model that we have built. So KNN is the model object. We are doing .predict on the Xtest to get the predicted values, and then we are using matrix.accuracy score to get the accuracy score of that model that we have created. Then we are printing the confusion matrix using the confusion matrix function. So here you see, like, what is the advantage of the common method creation. We are calling it just one line and passing the parameters to it, and the confusion matrix gets plotted from wherever this method is called. Okay, then we are printing the classification report. We are passing Ytest and Ypred, and we are also printing we are also extracting the probabilities. Here we got, I think here, right? Yeah, we got the predicted values, and here we are getting the probabilities as well. And this is the code to achieve that, and similar code we have used for logistic regression as well. Next, we are calculating the ROC AUC value. Using the ROC AUC score function, we are passing the Ytest and KNN probs. Remember, for getting the ROC AUC value, we need the KNN probabilities, not the actual KNN values or the predicted values. We need the probability values of it for getting the ROC AUC value. Hence, we are doing this. So once we get the ROC value, we are printing it. Okay, and then we are extracting the thresholds as well using matrix.roc score, and we are passing y-test and the probability values, the actual values. Once we get the threshold, we print the threshold as well. Post that, we are getting the ROC AUC using matrix.auc by passing the FPR and TPR, which we extracted here and here respectively, and then we are printing the ROC for the dataset, the value that we got here, and finally we plot the ROC AUC curve here, and then we append all the results into the DF results data frame again. So the result contains that we are appending all the values that we received here, that is accuracy score, the ROC value, the threshold, right, and then we are returning it finally from where it is, this method is called. So that's all about the KNN, K nearest neighbor classifier. Next we are going to see the model creation and evaluation for the common function creation for the tree models or decision tree models. Now in this session we are going to cover decision tree common method creation for model building and evaluation. So we have named the method as build and run tree models. We are passing the same parameters, the DF result, data frame, methodology, xtrain, ytrain, xtest and ytest. The criteria is set for Gini and entropy, and the scores we have defined an array to keep the scores, to store the scores basically. Now the objective is to create two different models here, right, and to store the results in DF results data frame. Now the two different models, the only difference in these two models will be the criteria. One will be created for Gini, one will be for entropy. Now what I am doing, criteria is an array, and scores was defined as a dictionary, not an array. So criteria is an array, right? For each values in criteria, that is for C in criteria, I am creating a decision tree classifier with a criteria as Gini, and next time it will run with entropy. The random state is 42, and I'm fitting the model on xtrain and ytrain. Then I'm predicting it on the xtest to store it in ypred. Then I'm getting the score and storing in test score, and similarly I'm getting the tree prediction values as well, right, probability value of the prediction. And then I'm getting the ROC AUC score using this probability, actual probability values and the predicted probability values and the actual y-test value. And finally I'm storing the scores in the test score. I'm storing this test score in the scores, right? Then I'm printing the score, and I'm printing the confusion matrix. I'm calling the same confusion matrix function, passing y-test and ypred. I'm printing the classification report as well here, and I'm printing the ROC value, okay, and then I'm using a matrix.roc curve function and passing y-test and tree press to get the FPR, TPR and thresholds. Once I get the threshold, I print it, and I also call the matrix.auc passing the FPR and TPR which we got here to get the ROC AUC value, and then I plot the ROC AUC curve here. Once all this is done, and this code base and the flow is quite similar to other common methods that we have created for other models, then I'm storing the accuracy, the threshold and the ROC value here, and returning the DF result data frame from where it is called. So in this way we can create the decision tree model on two different criterias in one compact code, and also do the evaluation for each of these criterias. In the next session we are going to cover random forest model. Now let's cover the random forest models. So for this we are going to name the common method as build and run random forest models. We are passing the DF result, methodology, xtrain, ytrain, xtest and ytest, the same parameters that we have used for earlier models creation. Then we are using, remember, random forest is an ensemble of multiple decision trees together. So random forest classifier is the method that we are going to use to create the random forest model. We are passing n estimators as 100, that is 100 decision trees, or 100 trees together will be used to build this model. The bootstrap is set to true. The max features is square root. That means every time we are creating our random model, so for each tree the maximum features that will be used is the square root of all the square root is the number for all the features that we have, right? So random state is 42. So now after this we are setting fitting the model on X-train and Y-train. Then we are using RF model, this is the model, dot score to get the score on this model that we have created. Post that we are using dot predict on X test, and finally we are printing the accuracy here. Okay, now let's see the actual class predictions. So we are using RF model dot predict on X test to get the predictions, right? And here we are printing the confusion matrix with Y test and RF underscore predictions. And then we are printing the classification report with Y test and RF predictions. So once we print the confusion matrix and the classification report, we print the probabilities for each class. So remember, we got the values here, predicted values. Now we want the predicted probabilities, which will help us to get the ROC AUC value. So we use the predict proba function here, and we get the probabilities. Post that we pass these probabilities and the actual value to the ROC AUC score to get the ROC value. Then we use the ROC curve function to get the FPR, TPR and thresholds, passing Y test and RF probes, which we got here. Now once we get the threshold, we print it, then we plot the same code that we used to plot the ROC AUC curve. Post that we store all these results like the accuracy, the ROC value, the threshold into the DF results data frame. Then we return it back. In the next session, we are going to cover the XGBoost model. Now let's create the XGBoost common method that will be used for both model creation and evaluation, like we have done for the earlier methods or earlier models that we have created in the earlier sessions. So we are passing the DF result, methodology, X-train, Y-train, X-test and Y-test, exactly like we have done for the other methods. And we are using XGB classifier, right, to create the XGB model. So once we call this with random state, we get the XGB model with default parameters here, right? And then we fit it on X-train and Y-train, and then we use this model to predict on the X-test and store the values on the Y-pred. Post that we used .score method to get their model score, and then we print the confusion matrix here and the classification report by passing the Y-test and Y-pred. Post that we also extract the probability predicted probability value for each of the values of X-test, and then we calculate the ROC AUC value by passing the Y-test and the XGB props as a predicted probabilities value. Post that we print this value, and then we also calculate the FPR, TPR and thresholds by calling the ROC curve with Y-test and XGB props. We print the threshold and we plot the ROC AUC curve here. Post that we store all these values like the method name, the accuracy, the ROC AUC value, and in DF results, and finally return it from where it is being called. In this way we create the XGBoost model and also do the evaluation. And then finally we'll move on to the last model, that is SVM model with the common method creation. Now let's start with the final method, model creation and evaluation, and this is SVM. So we have named the method as build and run SVM models and passing the same parameters, DF result, methodology, X-train, Y-train and X-test and Y-test. We use sklearn's SVC package to create the SVM model, and we are using kernel as sigmoid. Okay, and once we do that, we get this model and we fit on X-train and Y-train, and then we use the predict function on X-test to get the predicted values using the SVM model. Post that we get the accuracy score by calling the accuracy score function, and then we print it here, and then we print the confusion matrix and the classification report by passing the Y-test and Y predicted values of the SVM model. Then we also use this method, we run this classifier, right, SVC kernel sigmoid, exactly like this here. with probability as true. That means we want the probability values now. Here we got the predicted values and here we want the probability values. So hence we define it in this way. Once we get that, we use classifier.fit.predict proba. I have done this together in one line. You can break it up like we have done here. It's your choice. And we are passing the X test here. Once we do that, we get the SVM probs, that is the predicted probability values. And here we got the predicted values. Once we get the predicted probability, you can use the same to get the ROC value by calling the ROC score function and passing y-test and the SVM probs here. Once we get the ROC value, we print it, and then we use matrix.ROC curve function, passing y-test and SVM probs again the same to get the FPR, that is false positive rate, true positive rate, and the thresholds. Once we get the threshold, we print it here, right, and then we use matrix.AUC FPR and TPR to get the ROC AUC value, and then we plot the ROC AUC curve here, okay, with these lines of code. And finally we store the accuracy, the SVM score, and ROC value in the DF results data frame and return it at the end of the function from where this is being called. Now that we have created all the common methods for all the models that we want, next in the next sessions we are going to understand what are the different methodologies that we are going to use, against which we are going to create all these models. So we are going to use one methodology at a time. For each methodology we are going to create all these models by calling these methods, and then we see the accuracy, the ROC AUC value, the threshold, and then we move to a different methodology and see how well it performs in this methodology, all the models. In this way we'll go after one after another methodologies. So that's the reason we have created these common methods. Otherwise we have, for each methodology we have to write all these pieces of code again and again to create and evaluate the different models. Now let's talk about the different methodologies that we are going to use to create the different types of models using those methodologies. So one of the methodologies is repeated k-fold, and there is stratified k-fold that we are going to use. Apart from that, there are also other methodologies that we are going to talk about in subsequent sessions. So let's understand repeated k-fold and stratified k-fold here in this session. So repeated k-fold is the most preferred cross-validation technique for both classification and regression machine learning models. Shuffling and random sampling of the test data or of the data set multiple times is a core procedure of repeated k-fold algorithm, and it results in making a robust model as it covers the maximum training and testing operations. And in stratified k-fold, it is a cross-validation object is a variation of the k-fold that returns stratified folds. The folds are made by preserving the percentage of samples for each class. So this is very important. This is the main difference of stratified k-fold, that it preserves the percentage of samples for each class while doing the folds. So k-fold split dataset into k consecutive folds. So that's about repeated k-fold and stratified k-fold. Now we are going to use these two methodologies to create all the models that we have defined common methods of. Now that we have understood the repeated k-fold and stratified k-fold, it's time to put that in action. So the first methodology that we are going to use is repeated k-fold with cross-validation. So we have imported repeated k-fold from sklearn model selection, and then this repeated k-fold function we have to pass the parameters. The most important parameters are nsplit and nrepeat. Nsplit is how many splits you are doing for each of the repeats, and nrepeats is 10. So as a result, if I just okay, let's understand this first. So when I do the repeated k-fold with nsplit 5 and nrepeat 10, and I store it into RKF object, and then I do RKF.split passing x and y. So x and y, remember, x contains the entire dataset except the target column, and y contains only the target column. Here target is whether it is a fraudulent or it is a valid transaction, right? So when we do for train index, test index in RKF.split xy, we print it, right, the train index and test index, because these train index and test index will now help us to do the train test split. Okay, so when we print it, we get all this output. So for train, and this is test, and in this way 50 times it will execute, and 50 entries will be getting printed, all the indexes for train and test. Why 50? Because in split is 5, in repeat is 10, 10 into 5, 50. In this way, we get the train index and test index. Next, we use data frames ilog function. We pass train index and we pass the test index to get the xtrain CV and xtest CV. Indexes are basically stores the positions with the help of which we get the xtrain CV and xtest CV. And in the similar lines, we get the ytrain CV and ytest CV by doing y.ilog and then passing the train index and test index respectively. So as a result, at the end, we got xtrain CV, xtest CV, ytrain CV and ytest CV. So it's a clear train test split with repeated KFold on cross validation. Now once we get that, remember all the default all the models that common methods that we have created for all the models, we can now call each one of them by passing the xtrain CV and ytrain CV and then compare the results. In order to do that, so I've just added some headers for easy understanding. So I'm just calling the logistic regression with L1 and L2 regularization. So I'm calling build and run logistic models as the method name, right, which we have created for logistic regression, and this will cover both L1 and L2. I am passing the DF results data frame, which is currently blank because this is the first time we are running, and we are passing the methodology name, that is repeated KFold with cross validation, and we are passing xtrain CV, ytrain CV and xtest and ytest CV because this is what we have prepared, this combination for the repeated KFold. Okay, so once we do that, we print the time it takes to execute this or run and evaluate this model of logistic regression, and in this way we do similarly for KNN model. For decision tree model, the code is exactly the same. We are calling each of these methods, common methods for model creation for each of the models respectively, and we end with SVM. Right, once we do that, we execute. It will take a lot of time, and remember this is the exact reason why I am recommending you to run in Google Colab, because this execution might take, depending on your machine hardware configuration, it can take even an hour, or if you have good hardware it can still take around 20 minutes to half an hour. Okay, so once you but if you run in Google Colab, you can work on your own machine. It will not, otherwise your machine will stop you to use or other programs or activities if you want to do, and it might get heated up as well. So once you run this, you get the output similar to this, and let me scroll through and give you an idea of what it's printing. So first it is running the logistic regression. So here it prints the confusion matrix, and then it prints the classification report here. So this is the evaluation part started. This is for L1, and similarly it will do for L2 as well, right? And it's also printing the ROC curve that we have. All these things we have discussed while we are writing the code for the logistic regression common method creation, right? So exactly all things are getting printed one after another. And if you see here, the KNN model confusion matrix model creation done, then the ROC AUC curve, we see the AUC value here, and then it starts with the decision trees, prints the classification report, the matrix and confusion matrix, and then it goes for the random forest. In this way it covers SVM and XGBoost as well. Once it is done with the execution, I am just printing the DF results data frame, which contains the consolidated output of all this the models that have been executed on this methodology, that is repeated KFold with cross validation. Now see why we have prepared this type of data frame. This is how you can easily compare, right? You get the methodology, you get the model. For all this methodology, this number of models are executed. For each of the models, you see the accuracy, the ROC value and the threshold. Now looking at this table, you can easily say that the accuracy and ROC value we have for logistic regression with L2 regularization has provided the best results for cross-validation with repeated k-fold methodology or technique. So now in the next session we'll see another methodology, that is stratified k-fold, which we discussed in the earlier session, right, when we were discussing the theoretical part behind this. So let's see that in action in the next session. Now let's focus on the stratified k-fold methodology with cross-validation. So for that we need to import the stratified k-fold, which resides under sklearn model selection package. So in the similar lines, we create stratified k-fold with nsplit 5, and we have the SKF object, the stratified k-fold object. Once we do that, and using this we do the split on x and y, and we get the train index and test index. Then we further use the train index and test index to get the xtrain SKF CV and xtest SKF CV, and the ytrain and the ytest SKF CV, using x.ilog and y.ilog respectively on the train and test index. Once we do that, we have done with the train test split using stratified k-fold technique. And post that we use the XKF CV and subsequently the xtest and ytrain and ytest SKF CV to build all the models, right, where the common methods that we have created. So we first call the logistic regression with L1 and L2 regularization, passing the DF result data frame, the methodology name, the data sets, right, and we also try to calculate the time it takes to execute. And we do similarly for the KNN model, for the decision tree model, for the random forest model, XGBoost model, and SVM model. Okay, exactly the same code as we have seen earlier for the oversampling, for the earlier technique or methodology that we have used. The only difference is the data set here, okay, which we have prepared using stratified k-fold technique with cross-validation. Once we execute that, we get to see, again this takes a lot of time, it might take even 30 minutes. So once we execute it, we get all the confusion matrix and the classification report, ROC value, ROC curve, time taken for each model for all the models, okay, that we have created. Once we do that, we print the DF results data frame, which now consists of the repeated k-fold cross-validation which we have executed in the earlier session, and also the stratified k-fold cross-validation for each of the models. Now here, going through both, we can easily compare which model for which category performed the best. So after looking at that, you can come to a conclusion that the logistic regression with L2 regularization has provided the best result for cross-validation with stratified k-fold technique. And when we compare, so this is the comparison between this set only, stratified k-fold for all the models. But if you compare this with the repeated k-fold for all the models till now we have created, we see that the logistic regression with L2 regularization for stratified k-fold, that is this one, the 0.8, performed the best. Right, now that we have identified this, it's time that we go ahead and do some hyperparameter tuning to create the final model on logistic regression with L2 for stratified k-fold. So in the last session, we found out that logistic regression with L2 regularization performed the best with repeated k-fold technique. So it's time now to tweak some hyperparameters and bring out the best of that model. So we are again importing the linear model from sklearn package, and we also imported the k-fold. Next we used numc. Numc we are passing to CS with the np dot power of 10 with np of range of -10 to +10, and we're taking the list format. We are passing this list, that is the numc, to CS. Now CS is a regularization. We already discussed this while we were discussing the logistic regression part in the previous sessions. Penalty is set as L2 because we have found that L2 performed the best. Scoring on ROC, AUC, CV as CVnum. CVnum is a k-fold with nsplit 10 and shuffle true. and then the maximum iteration is 10,000, and solver is Newton CG, and total is 10. So again, all these hyperparameters, you can go through the link which I have shown earlier in the earlier session while we were discussing the logistic regression, to get a more detailed understanding on these hyperparameters. Right, so once we have the CLF object, that is a logistic regression object, we are doing a fit on it on X10 SKFCV and Y10 SKFCV. These two are, I think, the data sets for the repeated K-fold, right? And once we do that, stratified K-fold. Once we do that, we print the coefficients. Once we do the fit, after that we print the coefficients, the intercept and the scores, and then we predict on the X-test to get that predicted values, and also we do that predict proba to get the predicted probabilities values here stored. So after that, we can use accuracy, we can use this Y-test and the Y-pred to get the accuracy score of this model, and post that we import the ROC score from sklearn package, and we use that to get the ROC score. We also extract the threshold, FPR and TPR, and print the threshold, right? And once we execute this, we get these values. Accuracy score with L2 is something like this, 0.9988, and L2 ROC value and L2 threshold. And also we print the coefficient values here, and post that we create a data frame. Okay, here it's important one. So suppose after creating this object, after creating this model object, we see that we want to see what are the most important coefficients, or what are the coefficient values for each of the features, how each of the features contribute to the model, right? So first we created a data frame using pt.concat, and we provided all the column names, and then we are providing the coefficient values, right, with a np.transpose. Once we do that, we get this table. So we print it out, this table coefficients, and here we are setting the column names just. Okay, we are renaming the columns, and once we do that, we print the coefficients, and we get something like this. For each of the features, we get to see the coefficient value which the model has prepared, right? So at the end, we want to see the features which are more important, which are contributing significantly on this model. For that, I went ahead and plotted a bar chart, because with the help of this, it can be very easily we can understand which features are contributing a lot. So we are plotting a bar plot using SNS, that is Seaborn library, where X is the features and Y is the important coefficients or the coefficients, and data is the coefficient values. We have given some title. Okay, you can give any title you want, and then we are just plt.show to showcase it. So once we do that, we see that V4, V5, V11 has a positive importance, whereas V10, V12 and V14, and similarly this V16 and V17 as well, have a negative impact on the predictions. So in this way, we can plot the coefficient values, and we can see that which coefficients are having a positive impact on the model and which coefficients having a negative impact on the predictions. In the next session, we are going to cover SMOTE, random oversampling, and ADASYN, and we'll see that how we can balance the classes and we can perform the model creation or model building. Now let's cover the oversampling techniques here. We already know that the dataset that we have is not balanced. There are a lot of classes which are showcasing that the credit card transactions are not fraud, and very less percentage showcasing that they are fraudulent transactions. So in these cases, when we try to build a model, it's most of the time it favors the majority class in while giving the predictions. So it's important that we do some oversampling techniques, and we see that how the model performs using these techniques. So these are the three techniques which you can see on the screen. These are the techniques that we are going to use for oversampling. So one is random oversampler. So this involves randomly selecting samples from the minority class with replacement and adding them to the training dataset. So here minority class is basically the fraud transactions, which are very less in number, right, in our data set. SMOTE stands for basically synthetic minority oversampling technique. This is a statistical technique for increasing the number of cases in your dataset in a balanced way. So the module works by generating new instances from existing minority cases that you supply as input. This method generates synthetic data based on the feature space similarities between existing minority instances. So in order to create a synthetic instance, it finds the k nearest neighbors of each minority instance, randomly selects one of them, and then calculate the linear interpolations to produce a new minority instance in the neighborhood. So basically it creates, it generates artificial samples on the data which is minor, which has less in number. In our case, those are the credit card fraud transactions. So it analyzes those and it creates more instances of the minority class. Okay, now there is one more technique which is also very popular, that is ADASYN. So it stands for adaptive synthetic. It's an algorithm that generates synthetic data, and its greatest advantage is not copying the same minority data, instead generating more data for harder to learn examples. So that's all about random oversamplers, SMOTE and ADASYN, where it tries to generate more data for the class which is less in number. Again, that for that we are in this dataset, if you have to consider the dataset where the data where we have less number of fraud transactions. So those fraud transactions needs to be increased at par with the authentic transactions. Then the dataset will become balanced, and this process of increasing the number of transactions helps can be achieved with the help of SMOTE, ADASYN, or random oversampler. Post that, on the new or the updated dataset, we can train our models. So in the next session, we are going to see the random oversampler in action. Now that we have understood conceptually what is random oversampling, SMOTE and ADASYN in the last session, in this session we are going to cover random oversampler or random oversampling with stratified k-fold cross-validation. So as we have already understood, is the process of generating random samples on the minority class. So first we are going to import stratified k-fold from the sklearn model selection package and the random oversampler from the IMBlearn oversampling package. Post that, we are using the stratified k-fold and we are passing nsplit as 5, and we get the stratified k-fold object. We use this object to split on x and y, and then we enumerate on the same. For each train index and test index, we get the x train and y train and x test and y test dataset. So finally, using that, we use a random oversampler package, and then we pass sampling strategy as 0.5, that is 50%, and then we use this random oversampler object to fit on the x train and y train that we got from the stratified k-fold, right? And we don't do this on the x test and y test, because x test and y test will be only used for testing how the built model is performing. So all this random oversampling will be done on the train set only, not on the test set. Okay, so this is the piece of code which first does the stratified k-fold, okay, and then on the stratified k-fold we do the random oversampling. Okay, so post that, we convert the x over into a data frame with the data as x over and the columns with calls. Okay, the calls contain all the column names. Now that we have the x over and this is required to, this helps us in the model building part. So just giving the column names, and it will help us in all the models that we are going to build in the next. Okay, so once we have the x over and y over, we are going to use x over and y over on all the model building part using this strategy. The code base is exactly the same that we have used earlier for earlier model preparation using different strategies. So the code is same, only the difference is x over y over the data set, right? And once we do that, we prepare the logistic regression KNN decision tree random forest and XGBoost. I haven't considered the SVM here because what happens, you can go ahead and try, because I haven't used it. Reason being, it takes a lot of time to execute, right? And because SVM takes a huge amount of time when you have so large data set. So I've skipped it because once I have run it, I saw that it's not performing well enough, so I've skipped. But if you want, you can go ahead and use the same code base that I have used above, and just put x over y over x test and y test and run it. So once I run all this, all the logs gets printed below. It's the same things like the confusion matrix, the ROC curve, the ROC values for each of the models, and then I do the printing of the DF results, which contains all the earlier executed techniques results, as well as this one, random oversampling with stratified folds CV. And for all the models we have executed, and we found in this random oversampling with stratified KFold technique, XGBoost performed the best, right? And it has provided the best results for this category. In the next session, we are going to cover SMOTE, wherein we're going to see how SMOTE technique we can use to generate data, and on that data, how we can fit all these models and then compare the results with the random oversampling. Now let's cover the SMOTE technique in this session. So we already covered a SMOTE technique, the theoretical part of it. Now let's see it in action. So the coding part is pretty much similar to what we have seen for random oversampling in the earlier session. So first we are importing the stratified KFold from the sklearn model selection package. Then we are importing the oversampling from IMBlearn package. So we have created a stratified KFold method, and we are passing in split 5 with random status none, and we store it in a SKF object, that is a stratified KFold object. You can name it anything you want. And then I'm using SKF, the stratified KFold object, to split on X and Y, and then enumerate it for the train, and to enumerate on the train index and test index for each of the folds, right? And once we do that, we get the X train, Y train, and X test and Y test when we do a lock on the from the train index and the test index that we get here, right? And on the X train and Y train, we basically want to run the SMOTE. Okay, so SMOTE resides on the oversampling this package, right? Oversampling the SMOTE, and we use the SMOTE object to fit on the X train and Y train that we got here. Again, remember, we have to do this only on the X train and Y train, not on the test data, because this we are going to use to test the model that we are creating. So we do not want to oversample it. Okay, so once we do this fit, we get X train SMOTE and Y train SMOTE, and then we convert the X train SMOTE into a data frame with data as the X train SMOTE, and with the columns as we have stored all the column names, right, in the original data frame. Once we do that, we get X train SMOTE and the Y train SMOTE. Using these two, we are going to create all the models. Again, the code base is exactly the same, only the X train SMOTE and the Y train SMOTE has been added and replaced with the earlier names. Once we do that, we get the logistic regression KNN decision tree random forest and XGBoost model, and it takes again a lot of time to run, because you're increasing the number of total data set, right? So if you remember, there are around 1 lakh something data. Now because you have increased the undersampled cases of data to at par with the data of the data points of the credit card transactions which are not fraud. So that means you're increasing the overall data set. That means it's going to take much more time to execute all these models. So again, I will repeat, so please use Google Colab if you don't want to run in your machine. It's going to take a lot of time to execute. So once you do that, again, it prints all, for each of the model, it prints the confusion matrix, the ROC value, the curve, and then I print the DF results data frame, because here I am storing all the results. So as you can see, the earlier results are still here, and this is the section which got added, the highlighted one. And if you go through this section which I have highlighted, you will see that the XGBoost model, that is the last row, performed the best, and it has provided the best score for both the accuracy and the ROC value. So Now let's in the next session let's cover the ADASYN and the technique, that is ADASYN. Post that we are going to compare throughout the entire list and see which model is performing the best in oversampling cases and overall which model perform the best. Now let's talk about ADASYN oversampling technique. We already discussed this theoretically. Now let's see this in action. The code is almost similar to SMOTE technique that we have seen in the earlier session. So we are importing stratified KFold from the sklearn model selection package, oversampling from IMBlearn package, and then we are doing the stratified KFold within split 5, and we are storing the stratified KFold object SKF into SKF. And then we are using SKF to split on the X and Y and enumerate it on, okay, so once we split on X and Y, we get the train index and test index, and we are enumerating it over and over to get the X train and Y train. Okay, once we do that x.log and y.log on the train and test index, we'll get the X train, X test, Y train and Y test. And then on the X train and Y train, we are going to do ADASYN, which resides under oversampling package. And once we get the ADASYN object, we are using it to fit it on the X train and Y train to get X train ADASYN and Y train ADASYN. So then we are using X train ADASYN to convert into a data frame using data in a particular format in this way, which we have discussed in the earlier session. And then we are using X train ADASYN and Y train ADASYN to build all the models. The code base is exactly same, so I'm not going through again. So here we have kept X train ADASYN and Y train ADASYN. Okay, once we do that, here is the output of all the models. Okay, and then we print df results data frame, and let's just look into the ADASYN part, only this part, and we see that the XGBoost, again the XGBoost, the last row, has performed the best for the ADASYN oversampling with stratified KFold technique. Okay, so in most of the cases we see XGBoost performing the best, hence it is very popular in all the machine learning competitions and also in Kaggle platform. And at the same time, you might have you might be thinking that why we are using stratified KFold with ADASYN oversampling, random oversampler and SMOTE. The reason being, we first want to do split equal division of split. That is, when we do a split, we want both the splits having equal amount of both the classes. On that, when we do ADASYN, it works best, right? And so if we have to draw an overall conclusion on all the oversampled techniques that we have used, that is a random oversampler, the SMOTE, the ADASYN, we will see that XGBoost model with the random oversampling with stratified KFold CV has given us the best results among all the oversampling techniques, that is SMOTE and ADASYN. So we'll use that model or that data set of random oversampler with stratified KFold to further tune the XGBoost model by tuning the hyperparameters, which we are going to cover in the next session. So in the last session, we found out that the XGBoost model for random oversampler with stratified KFold performed the best. So let's do some hyperparameter tuning on that model using those techniques. So we are importing the XGB classifier from XGBoost package, and then we are importing also the grid search and the randomized search CV from the sklearn model selection package. We are setting these hyperparameters. Okay, so max depth, minimum child weight in estimators, learning rate, gamma, subsample and cold sample by tree. Again, if you want to know more about the details of these hyperparameters, you can refer the documentation for the XGBoost. You can know all this in detail. And then we are using randomized search CV to go through each of these parameters and find out which parameter perform the best. So if you have a lot of bandwidth and you have a lot of time, you can use grid search CV, because it will try out all individual combinations, that means a hell amount of combinations here, but because I don't have that so much of computational power, so that's the reason I've used randomized search CV, because in that case it randomly picks up certain values and checks whether it is that those parameters are performing the best. So it is always recommended to use grid search CV if you have the computational power and time. Okay, so in randomized search CV I'm using estimator is XGB classifier because it's an XGBoost model. The base score we have set as 0.5, booster as GB3, and rest of the parameters. Okay, the call sample by tree, call sample by node, and the objective is binary logistic because we have either either the credit card is a transaction is a fraud or it's a legitimate, and the other parameters as well, right? And then in the param distribution we are setting as param test all these parameters, right, all the hyperparameters with n iteration as 5 and scoring on the RUC AUC, and n jobs -1, which is this means it will run parallelly, and CV cross validation is 5. Once we do that, we do on gsearch.fit x over and y over. Remember, x over and y over are the data set we have got after random oversampling with stratified KFold. Once we do the fit, we print out the results, the base params and the base score. Okay, and if you scroll down, this will take a lot of time to execute. So these are the base params, okay, that we have got, and this is the base score. Okay, using randomized search CV. Again, if I execute this the second time, this accuracy as well as this hyperparameter values might change because we are using randomized search CV. And next time maybe it will pick random other combinations. For that it might give different values and might give a different best accuracy. So I have tried out these hyperparameters. Okay, and because I've run it multiple times, so I've tried out multiple hyperparameters and I found that these hyperparameters perform the best. Okay, so I've set these hyperparameters here, whichever I got from above, and then I'm fitting on x over and y over, and then I'm using the clf.score to get the score of it, that is accuracy, and then I'm also predicting using the predict proba to get the probabilities. With the help of that, I'm getting the ROC AUC score and also getting the thresholds FPR and TPR. Finally, I'm printing out the accuracy ROC value and the threshold here for the XGBoost with random oversampler stratified KFold technique. So in this way you can do hyperparameter tuning, which takes a lot of computational bandwidth and time. Okay, so once you are done with this, let's move to the next part, is that how we can print the important features of the base model to understand the dataset. Remember, we have done a similar exercise once we have done it for logistic regression in the earlier session. Now this is for XGBoost. Let's see how we can achieve this as well. Now that we have prepared the XGBoost model after doing the hyperparameter tuning, it's important that we can extract the best features from the model that we have created. So I've created an empty array with the name important underscore variable, and for XGBoost model, so CLF is the XGBoost model object, right? For XGBoost there is a functionality like .feature underscore importance, with the help of which we can get all the important features. Okay, so now I look through each of the features, important features in the feature underscore important list, and I put it into this array which I have created, right? And post that I print the top feature which is contributing significantly to the model, and the second and the third one as well. So here I have done the important variable dot index np.sort clf.feature importance -1. This actually means that after getting the feature importance, it basically gives the feature importance in a descending order. The coefficient which has the highest value comes first. So when I do -1, I get the last value in that array, so hence I get the top variable. And similarly for the second top var and the third top var, I do -2 and -3, that is the second last and third last. Once I do that, I get to see the the index of the top and the second and the third variable, and in this way you can extract the important features of the best model, in this case XGBoost, and then I calculate the AUC ROC or the ROC AUC value or the score. So I pass the y-test and XGB probes to get the ROC value, and then I print it and also print the threshold here. So this is the final model. XGBoost ROC value is this and the threshold is this. In the next session, let's conclude of all the observations that we have for all the models that we have created, against all the techniques that we have used. Let's see which model performed the best. Okay, so let's now conclude with the observations that we have. So we have tried out different techniques. For each of the techniques, we have created so many models. So just to reiterate, we have used techniques like stratified KFold, then we have used SMOTE, ADASYN, random oversampling. Okay, of all these techniques, we have executed the SMOTE, ADASYN, and the random oversampling. These are the oversample scenarios. So in the oversample cases of all the models that we have built, we found that XGBoost model with random oversampling with stratified KFold CV gave us the best accuracy and ROC on the oversample data. Hence, we have done the hyperparameter tuning and got these matrices, and also with this hyperparameters, we have created our final model on which we have done the feature importance, which I have covered in the earlier session. But of all the models that we have created till now, using all the strategies, we found that the logistic regression with L2 regularization for stratified KFold cross-validation technique without any oversampling or undersampling gave us the best result till now. Okay, so in this way you can explore other techniques as well, or other models as well. Okay, so we have covered for credit card fraud detection, even though you have a very unbalanced data, how you can still use techniques other than oversampling or undersampling and still get a very good accuracy like we have got for logistic regression with L2. And also with oversample cases that we have built for ADASYN or the SMOTE techniques or random oversampling, how you can do the same using mixing the stratified KFold technique with it. So in this way you can you have seen that all these techniques have given us different accuracies, and of all the techniques, which model perform the best. Okay, so in this way you can cover other models as well. You can try out SVM for some of the techniques we haven't used SVM. Hope you have learned something new here, and hope you can implement this and create your own credit card fraud detection project for yourself. Thanks for watching.